The net pitching moment about the lateral axis is due to the contribution of each of the component surfaces. A fact the examiners might be interested in is that the wing camber has no effect on longitudinal static stability. This is because the pitching moment about the aerodynamic centre is always nose down, regardless of angle of attack. The contribution of the wing has already been explained in previous lessons. But to remind you, the wing is destabilizing because the aerodynamic centre is forward of the aircraft CG. At the small angle of attack used in the cruise, the fuselage acts as a symmetrical aerofoil. The reduction in pressure on the top is the same as the reduction in pressure on the bottom, with an area of stagnation pressure at the nose. Under these conditions, the fuselage generates no pitching moment. Any change in angle of attack generates an aircraft pitching moment, which is destabilizing. The pitching moment is generated by the change in pressure distribution on the fuselage and nacelles. As we have already established, the tailplane is the aerofoil that provides the stabilizing influence to the aircraft. This is due to the stabilizing pitching moment it generates when the aircraft is subjected to a change in angle of attack. For simplicity, the first explanation of longitudinal static stability assumed a gust would give the same change in angle of attack to the tailplane and the wing. In practice, the airflow at the tailplane will be affected by the airflow from the wing trailing edge, as illustrated, and the tailplane will experience a smaller change in angle of attack than the wing. The designers ensure the tailplane can always generate the appropriate stabilizing moment by attaching the tailplane at a smaller angle of incidence than the wing. This is called longitudinal dihedral. The illustration shows a wing incidence of 4 degrees and a tailplane incidence of 2 degrees. If a gust of wind increases the angle of attack by 4 degrees, the change in wing lift will be 100%, whereas the change in tailplane lift will be 200%. The graph shows a typical build-up of components and their effect on longitudinal static stability. The wing is destabilizing. The wing and the fuselage together are even more destabilizing. The tailplane contribution is very stabilizing. And when we consider everything together, the aeroplane has the required degree of longitudinal static stability. Notice the location of the CG in the illustration is listed as 20% MAC. The mean aerodynamic chord is used as a reference point from which the location of the CG is measured as a percentage. The higher the percentage, the further aft the CG. We can use the graph to show the effect of CG position on longitudinal static stability. With the CG at 10% MAC, the aircraft is stable. The aircraft is less stable with the CG at 20%, and even less stable with the CG at 30%. 40% MAC is the neutral point, and with the CG at 50% MAC, the aircraft will be unstable. The neutral point and 50% MAC are shown with a dashed line, because operationally the CG must never be positioned outside the aft CG limit. The effect of thrust on longitudinal static stability will be greatest at low indicated airspeed and high thrust, such as during takeoff and the approach to landing. The vertical location of the thrust line defines one of the contributions. The illustration shows an aircraft with pod-mounted engines beneath the wing. Because the thrust line is below the aircraft CG, an increase in thrust will produce a nose-up pitching moment, which is destabilizing. A propeller located forward of the CG will also contribute a destabilizing effect. The change in momentum of the prop wash will generate a force normal to the plane of the propeller. It has already been stated that a stable aeroplane will resist displacement from equilibrium. The control surface displacement and the control forces should reflect the stability of the aeroplane and provide suitable reference to the pilot for precise control of the aeroplane. The effect of elevator deflection on pitching moment is illustrated. The elevator is neutral to the tailplane, and the aircraft is flying level at a given lift coefficient. A momentary increase in angle of attack generates a stabilizing nose-down pitching moment. Reset the graph. A momentary decrease in angle of attack generates a stabilizing nose-up pitching moment. Reset the graph. The illustration shows a certain amount of static longitudinal stability, with the elevator at neutral. The aircraft is maintaining level flight by increasing the angle of attack as the indicated airspeed is decreased, until once again it is in equilibrium at a lower airspeed. To hold this angle of attack at a lower airspeed, the elevator must remain displaced at a position 10 degrees up from neutral. A momentary increase in angle of attack generates the same stabilizing nose-down pitching moment. Reset the graph. A momentary decrease in angle of attack generates the same stabilizing nose-up pitching moment. Reset the graph. The illustration has shown the same amount of static longitudinal stability with the elevator at 10 degrees up as it did with the elevator neutral. This is easily seen at a glance from the fact that the two plots are parallel. Now the aircraft is continuing to maintain level flight by decreasing the angle of attack as the indicated airspeed is increased, until once again it is in equilibrium at a higher airspeed. To hold this angle of attack at a higher airspeed, the elevator must remain displaced at a position 10 degrees down from neutral. A momentary increase in angle of attack generates the same stabilizing nose-down pitching moment. Reset the graph. A momentary decrease in angle of attack generates the same stabilizing nose-up pitching moment. Reset the graph. The illustration has shown that the same amount of static longitudinal stability will be obtained with the elevator at 10 degrees down, neutral, and 10 degrees up. Elevator position does not affect longitudinal static stability because only the change in lift is considered. We can now consider the effect of CG position on elevator deflection. Please note that the vertical axis of the graph now represents elevator deflection. With the CG at 10% MAC, the aircraft will have a lot of longitudinal static stability, and a large up elevator deflection is required to maintain a given lift coefficient. With the CG further aft at 20% MAC, there is less longitudinal static stability, and less up elevator is required to hold the same lift coefficient. With the CG even further aft at 30% MAC, there is less longitudinal static stability, and less up elevator is required to hold the same lift coefficient. This animation illustrates the increase in aircraft controllability with an aft CG. Please note that the horizontal axis of the graph now represents indicated airspeed. All aircraft must have something called stick position stability. This means that the aeroplane must require the stick to be moved aft to increase the angle of attack, and trim at a lower indicated airspeed, and to be moved forward to decrease the angle of attack and trim at a higher indicated airspeed. While maintaining level flight, as the indicated airspeed is reduced, the elevator must be moved up. This requires the pitch control in the cockpit to be moved aft. Reset the graph. While maintaining level flight, as the indicated airspeed is increased, the elevator must be moved down. This requires the pitch control in the cockpit to be moved forward. Please note that the vertical axis now represents stick force. In addition to stick position stability, all aircraft must have stick force stability. This means that a push force must be required when indicated airspeed is increased, and a pull force must be required when indicated airspeed is decreased. The plot shows the stick force gradient with the aircraft in trim at low indicated airspeed. To maintain a reduced indicated airspeed of, let's say, 10 knots at low speed, a certain pull force is required. The plot now includes a stick force gradient with the aircraft in trim at a higher speed. To maintain the same 10 knot speed reduction from trim speed at a higher speed, a pull force is still required, but the required pull force is smaller. We can now consider the effect of CG position on stick force. From our previous studies, we know that moving the CG forward increases longitudinal static stability. With the CG at 30% MAC, a speed reduction requires a small pull force. With the CG at 20% MAC, the same speed reduction requires a larger pull force. With the CG at 10% MAC, the same speed reduction requires an even larger pull force. Moving the CG aft decreases the stick forces required to displace the aircraft from trim speed.